I'm from Oracle. This is about NVM Direct. It's an open source non-volatile memory API that I developed. I haven't worked on for about 4 years. I do other stuff now. This is a big disclaimer. Anything I show you here might not happen. I mean, I'm going to tell you some things that we've done at Oracle, but it's quite possible they will never be released. Only I'd be very sad. Okay, so we've developed an NVM API consisting of C language extensions and a library. And I'm very much of the belief that without language extensions, we're not going to be able to write reasonably bug-free, readable code, maintainable and readable and bug-free. Anyway, so this gives you NVM Direct. It gives you load store access to non-volatile memory. There's sort of 3 big chunks. We have region files where it's a DAX file, right? You map it in and stuff. Has a special little format that makes it be one that NVM Direct understands. We provide transactions so that you can do updates to arbitrary amounts of data in a transaction, and you have locks so you can do it multi-threaded. And we have a heap there where you can allocate chunks of memory and call them a struct, a persistent struct. And the whole idea is that this simplifies coding, reduces bugs, and should try to catch corruption early. That's a big thing. I believe that corruption is going to be one of the biggest problems we have. And you can do things with this library. You don't have to, but you can do things with this library to validate that the pointer is good when you use it. You can find the source, open source in NVM Direct. And there's a pre-compiler that the guys haven't really released yet. I guess it's still a little bit of work on it. That will become open source. It's based on Clang. Okay, so I'm just going to give you a little short description of what we're doing at Oracle with it. We've taken NVM Direct as the open source version and modified it so it can work within Oracle, because Oracle's got a lot of conventions like thread death doesn't take out your process kind of thing. So it had to be reworked. It also, I'm sure they've done some performance improvements. I didn't have a lot to do with that. Mostly what I've done is define an API. And what it's going to let you do is have a single instance database that can have some of its files, any subset of the files you choose, in NVM and mapped directly into the address space of the Oracle kernel. So you can put your data files, your online logs, and control files, because they're performance critical, right in memory. One of the things that you can do, because it's in memory, is you don't have to read off of some media, copy it into DRAM. We can have buffer headers that point directly at the NVM. We do that if you're just doing reads. For updates of a block, we really have to update blocks atomically, so we make a copy in NVM, or in DRAM from the NVM, modify it, and then write it back out to the file, the data file, or whatever. And it's a lot like BTT in the way it does pointer switches. And rather than other techniques for atomacy, Oracle depends on data block writes being atomic almost always. I mean, we have recovery stuff if you get a corrupt block, but if it happens on every reboot, it's hopeless. Okay. And right now, we're evaluating performance, finding lots of performance bugs, making things better. That's what we're doing. So the point is, this is real. People are using it. We've made some pretty big data structures that aren't anything that are very straightforward data structures. And one of them things, there's a part of the GitHub thing is something called direct mapped file, DMF. And that uses algorithms very much like BTT that were the grandparent of the algorithms that we used in the kernel. So you can look at that if you wish. So corruption is going to be a problem. We get, everyone here I'm sure has seen a panic or a blue screen or both in their lifetime, right? I mean, it happens. And rebooting doesn't work in NVM, as we all know. So I think that preventing problems and catching them really early is critical to the success of NVM. Oh, I'm sorry that I keep calling it NVM rather than PMEM. I
think we all understand.
Yeah. So the primary focus of this design is to reduce bugs and catch corruption early. And it's also to make it easy to use structs in NVM as it is to use structs in DRAM. In other words, the idea is you don't have some limited set of data structures. You get to go invent any data structure you want with this API. And the data structure we used in the Oracle kernel for this stuff isn't anything that would have been doable with like these atomic pointer switches or whatever. It's more complex than that. Anyway, region files. This is kind of the basics of how do you get NVM into your address space, right? You have to have a DAX file system. You have NVM formatted for API. Okay, so we have to have the file that you use has to be a specific file. It can't be an arbitrary file. It has to have the first 16 bytes have to be a specific value. That's some random number that I got out of random.org one time. So that is the way we recognize it. Then you also have another one of those numbers that is represent the application that the application can say, oh yeah, this is a file that I know how to interpret. So that's part of it. The region file has two sizes. One is a physical size, which is how much NVM is actually stored in the thing, is available in the thing. The other is a virtual address space. You really generally want the virtual address space to be bigger so that you can grow things as you want. And one of the things people often say is, I need to have multiple files of NVM, and I need to have pointers between them. But you can't really do pointers between NVM regions atomically very well. So what we do instead is you have a big address space, and you can have various extents at arbitrary offsets within there, and you can grow and shrink each extent independently as time goes on. And this gives you pretty much the same effect as multiple files. But of course, you wind up burning a lot of virtual address space just to be. But, you know, there's a lot of it. Hopefully it'll be enough. You can get multiple regions all at once, but you can't have pointers between them. But you can have them, and you can't do atomic transactions between them. You can, you can see some things we can do between them. Okay, NVM transaction. This is kind of critical. The ability to update arbitrary amounts of data atomically. And the way you do it is you start off with an @ sign, and that @ sign kind of is the character that kind of means transaction stuff. And then you have a region descriptor, which is like a file descriptor, small number. And then you have a block of code following it. And that block of code is a transaction. And if you exit that through a normal C things, like you jump or return or whatever, that commits the transaction. If you crash in the middle of it, that block, or if a long jump blows through you, then it gets deleted. It gets aborted. You can also explicitly abort it if that makes sense for whatever you're doing. I've personally never found a case where I wanted to explicitly abort, but it was easy to just sort of make the subroutine name known. You know, that's all it is. We have a new assignment operator. We'll get a little bit more detail about it later, but it's either an @ sign or a tilde, and then your regular operator that modifies memory. And that tells you that this is something that's going to be, is in NVM, and you have to use that kind of an assignment for NVM. So the compiler, or the pre-compiler actually, knows what operations are NVM and knows to add the flushes and to add other checks if it can do it. Another interesting thing is that the locks that you use for managing your data structures in multi-threaded, they're NVM locks. They're part of your transaction. They're persistent. And they aren't owned by the thread. They're owned by the transaction. Now, a transaction is kind of owned by a thread when it's running, But if you crash, the thread goes away, but the locks don't. And that's important for recovery because when you come up, you have all these multiple transactions potentially, and some of them might be operating on some data structure that some other has to go and modify and get the lock on to modify to do the recovery. And we'll get into why. And so that's why, yes?
Transaction structure is log, or is it the object? Locks, are those in the table, the log, or the object?
There's it's a log. It's a bunch of blocks linked together. Really, in real life, it's only one block because transactions aren't that big. And it's undo. It's undo, not redo. That's a big decision. So every time you do a store that's going to be transactional, you create a piece of undo into the log, and then you do the store. And you have to persist the log, and that takes 2 persists to make the undo exist, and then 1 to make the data that you're modifying exist whenever you've gotten around to a place where you need to do that. And I really want EADR. Okay, locking. You can have an NVM mutex be a member of a struct. It can, and I implemented both shared and exclusive locking, and wait, no wait, timed wait, those kind of obvious things. They're in the as I just said, their locks are part of a transaction. It's a record in the transaction. Locks are only released at commit or abort. And the reason for that is that if you take out a lock on something and modify it, you're generating undo, which is a potential future store. So you got to hold on to the lock until you're not going to do that store. In other words, when the transaction commits, you're not going to apply the undo. When it aborts, you did apply the undo, and so then you can drop the lock. So when you do the abort and you roll back the transaction, you start at the end of the transaction, undoing everything until you get to the beginning. And when you hit a lock, you release that lock, and because that lock was clearly covering stuff that was later in your transaction. Okay. Because I worry about deadlocks, I said that you have to have a lock level for every mutex, and if you don't get them in the right order, you didn't think enough about your code. So you can only get locks at a higher level. Of course, it doesn't interact with other locks in the world, so you could still have deadlocks.
If you crash in the middle of that chain, come back and you start from that point.
Yeah. Oh yeah, I mean, applying undo also vaporizes it, You got to change pointers so it doesn't exist. So we have that deadlock protection stuff. Okay, nested transactions. Now this drove me crazy until I figured out how to do this. I didn't know about the word nested transaction. I had to invent this. A nested transaction is something that you probably mostly know about it, I didn't, is something that you can commit or abort independently of the parent transaction. And so once it commits, it's committed even if the parent aborts. So, and that means that since a nested transaction is commits or abort independently, when it commits or aborts, locks it acquired are released, and when it commits or aborts. And of course, the undo is undone too. But basically, the way it works is all the undo for the nested transaction is tacked onto the end of the parent transaction, and then rolled back when it commits or aborts. Well, rolled back if it aborts, and thrown away if it commits. Yes.
How can transactions be nested if they are completely independent from each other?
What do you mean by independent?
It's written there in the first line. Nested transaction commits or aborts.
It commits or aborts independently, yeah.
Yeah, but then what does it mean that they are nested if it's independent? It means one active, so the other one's active.
In other words, the parent transaction starts a nested transaction. That transaction proceeds until it commits or aborts, and then the undo is thrown away for the nested transaction, so that now you're back in the parent transaction. Anything you do is part of the parent transaction. Okay?
Do you also have the ability to have a way of nesting a transaction where it becomes part of the outer transaction?
Nope, never thought about that.
Okay, because there are both models have been in use in
Okay.
relation systems.
Yes.
Yeah, I mean, so going back to this point, we actually felt that the nested transaction is easier understood if it just blends into the parent transaction.
Yeah, I've been told that people don't understand nested transactions, and that just kind of
Well, there are
frustrates
both
me.
options, though, and the thing is, if you have, they're often called open and closed nested transactions. And if you have one transaction that's being used in a library that then gets invoked inside another transaction, sometimes that other transaction wants to have everything happen all at once. Sometimes it's necessary to do something as a side effect to avoid, say, locking contention, to have an open transaction where it happens on its own and then the other one carries on. So they both have their uses.
This is open nested.
Yeah.
I don't have closed nested transactions. Now, maybe I should have, but I didn't.
For composition, because it means that you can use code to run to build transaction and have it happen inside your main transaction.
Sometimes that could be a whole other topic.
Yeah. Real quick.
Transactions, in the sense that you're using the term, do they involve isolation between threads, or are these durability transactions?
Durability, the isolation you get through by using your mutexes. It's the way you do things in C.
Right. When I hear a database guy use the word transaction, I think you might mean isolation. Right, that's what I thought.
I don't know SQL. I couldn't do that. The thing that makes it nested is just the fact that there is a parent. And it turns out that starting a nested transaction is a lot quicker than starting a parent transaction, a base transaction, whatever you call it. Because for starting a brand new transaction, when you don't have one, requires allocating a transaction. And so it makes sense sometimes to have a process that starts a parent transaction, never commits it. And then its transactions, if it does lots of transactions, it becomes quick. That's one thing we discovered quite recently.
There's also partial rollback, so it's a good thing.
Yeah, well, there's also a rollback operator that you can set a save point and then roll back to it without a transaction.
It's very useful.
Oh, maybe that's an open transaction or a closed transaction. I don't know. What do we got next? Pointers. The C extensions let the precompiler know which operations or which pointers point to NVM versus pointing to DRAM. And when you have an NVM pointer, rather than saying star PT or whatever, you say caret PT or whatever. And that means that this thing points at NVM. When you do the arrow for struct reference through a pointer, you use equal greater instead of minus greater. And similarly, for the address of operator, you use percent instead of @. And that's how you set your pointers up so that things work. And the compiler is checking this stuff for you so that if you actually tried to, at compile time, you can do a lot of checking that says, oh, you're pointing to persistent memory, but you used a star. That doesn't work. So that's part of the syntax helping you do the right thing. And then here's what I was talking about, the transactional operators. See, @ equals instead of equals, tilde equals instead of equals. There are some, it's quite common to have stores in persistent memory that you don't need undo for. And generating undo is really relatively expensive. The most obvious and common case is you allocate something out of a heap, you go and you initialize it, you put stuff into it, and then you commit your transaction. Well, if your transaction doesn't commit, all that stuff you stored in there, it doesn't matter because it's going to, when you roll back, you're going to release the memory that you allocated. The parent transaction has to release the allocation that was done. We'll get into that, how that works. How much time?
You have about 10 minutes.
Okay. Persistent structs. If you want to allocate it out of NVM, it's got to be declared persistent. It's a keyword. There are things you can say about a struct, like you can say, oh, I put this random number I got from random.org or some true random number generator, and it's going to appear at the beginning. I want it to appear at the beginning of this thing. And that can be used to verify pointers or pointing to what you expect them to point to. the big thing about pointer, the way I implemented pointers to NVM was as self-relative pointers. That means you take the address of the pointer itself and you add its contents to its address, and that's where it points. And this means a null pointer would point right to itself, and there are cases where pointing your pointer to itself are useful, like empty lists or something like that. So a 1 represents a null pointer. And I was very confused about this until I found out that Boost does it this way, so I didn't invent that. And then the precompiler knows that you've got a pointer from NVM to NVM, and it does the arithmetic, outputs the code to do the arithmetic for you. And if you do a store, if you store the address of something in NVM into a pointer that lives in DRAM, that pointer will get a normal pointer. If you store it into a pointer of the same thing into another persistent struct in NVM, it becomes self-relative. And if you try to store between two different regions, that's an error, because you can't do transactions between regions, mostly. I found it's very useful times to have a transient, which means I know this is NVM, but just pretend it's DRAM so I can do things with it. I can point to DRAM. And then you have to come up with a mechanism that says, oh, we've been remounted since this pointer was stored here, so it's no longer valid. That has to be something that is kind of up to the programmer to do. And there's every time you map in a region file, it gets a counter bump that's easily available, so that you can say, oh, and you can save that counter with this thing that's got transients, and then compare them and say, oh, this thing's stale. Any transients are stale. Okay. Oh, here's an interesting thing. One of the things I did was, for every persistent struct, there is in the executable a description of that persistent struct. It describes what the types are of all the different fields, how big they are, and if it's a pointer, it points to some other thing, tells you what that type is. And so you can fundamentally, we could write a utility, but we haven't, that would scan through, if it's got all these declarations, it could go scanning through all the files, the things, and find all the pointers, find missing pointers or corrupt pointers or whatever, and follow all the types, which I think would be very useful for debugging corruptions. Maybe even you could patch them. So came up with this thing called a USID. You know how I've talked about 16-byte random numbers? That's a USID. Stands for Universal Symbol ID. You can assign a USID to anything that's an external in your program. Any external location that's in your code, you can give it a USID. And what this means is that you can recompile and change your executable, but if you keep the mapping of USIDs to types the same, then you can, with a different executable, you can use these as persistent pointers into DRAM or into your executable, which could be a pointer to something you declare in DRAM, such as a global struct of some sort. At runtime, at startup time, we take all these USIDs that have been part of the code, and we build a hash table so you can quickly go from some USID you find. For example, the header of the structs that are declared to start with a USID, that points to their type declaration, so that you can then go through and verify the struct really is the struct it says it is. And if you know what limits there are on various fields, you could check that. Okay. Time? We add code to verify the USID before using a pointer to something. And you can use a function pointer. Oh, heaps. When you create a region file that has a base heap, additional heaps can be added as in new extents, or you can have an extent that's just managed by your application. You can add it, you can grow heaps as long as you have some virtual address space after them. When you do an allocation, you have to point to these struct types, so that you don't say malloc and then you give the size. you say allocate out of this heap, and it's for this type of struct, and I want this many of them. And you can also say it ends in a zero length array of this, it's going to be this many entries in that zero length array. And free takes, okay. It's very important that an allocate or a free that in a parent transaction that doesn't commit gets rolled back. And I think we're about to do that. That is a really critical thing. It's called on-abort operations, on-commit operations. There's also an on-unlock operation, which is not part of the slide. One of these operations, it's a record in the undo log. It has a USID to point to the function that executes it, and it's got some arbitrary persistent struct there with it that are the arguments to that function. And so it becomes something that, and it gets executed. That function gets called within a nested transaction. If it's an on abort, when you roll back through that, it gets called. If it's an on commit, then we go through all of the on commit operations and execute them. If you die in the middle of this, you do it again. And what committed, and what abort, and maybe you'd aborted one of your on commit operations that you then have to start over again and so forth. And what this is really important, because what it lets you do is create logical undo for an operation such as allocation from a heap. And then it turns out the exact same function that lets you do allocation also is used for free, but it's an on commit operation instead. And they have to kind of be the same. And you often wind up with pairs like that. And so the on commit operations are done at commit time after you've done all of your lock clean out, then you do your on commits. And if you crash, they'll get all called again because recovery knows to do that. One of the reasons that locks have to be persistent is because these operations typically, like the most common one is allocation from a heap. It has to get a lock in the heap. So the locks have to be acquired during recovery. And you got to make sure you're not contending with somebody else that's got that lock that's also in recovery. And that's what that's why locks have to be persistent, owned by transactions, not threads. I tried to come up with a way of doing in-place structure upgrades that are sort of like you can switch USIDs and stuff. It's probably better to just get to questions.
So for your NVM regions file,
Yeah.
It seems like it's just another sparse file format.
Yep.
Is it possible to reuse an existing one like QCal or some other such thing, and then maybe modify
Well, what was impossible was for me to know about that or think about that.
Okay. So maybe something you need to consider reusing.
I don't even know what you're talking about.
Okay.
QCal.
There are sparse file formats that already exist, like for example, disk images for VMs. You may be able to
DAX files can be sparse, right?
Well, he's talking about a copy on write idea where a bunch of VMs start from the same file, but then they get copies of their own changes.
Oh, that's like snapshots.
Or
Yeah,
VMDK,
but at file,
or
yeah.
there's a bunch of formats
Yeah.
for sparse files. Just an idea.
I think this is for a different purpose, but I don't know. Any other questions?
Yeah, he's got to know this.
Okay.
Copy on write.
Another idea that popped up, you added a lot of operators
Yeah.
to differentiate between a persistent operation and a non-persistent operation. Would it be possible to modify the pointer, say set a high bit in the pointer value, and then use that to determine if your address is for persistent memory or non-persistent?
That didn't seem like a good idea. It's like that runtime performance hits. This is all compile time.
Even at compile time, you can see what the value of the pointer is.
I don't know. You think about it yourself, I guess. What?
So the compiler, the new compiler syntax, the new language syntax for persistent versus non-persistent data, does that mean that existing libraries for dealing with non-persistent data, like I'm thinking of the standard library Sterling, right? Do you need to recompile a new version for persistent memory?
No, you have to write a new version.
You have to write. Okay, so basically all the pointer-based code that we have to rewrite all that?
Yeah. Isn't that the case for everything that we've ever talked about? No?
No, I mean, for your library, yeah, but not for
Okay.
You can use libc with RDK, of course.
What do you mean by you can use libc?
You can take something that's in persistent memory and call strlen on it.
Oh,
Why wouldn't you?
Even better, in NVM C++, you can even use the STD algorithms
Yeah.
on top of persistent data structures. So, for example, you can imagine to use STD sort on top of PIRL vector, and we make that work.
I bet you could cast and do that because it would work. You're right. Maybe we should come up with a way of allowing that.
In your language, I'm sure you can cast it, yeah.
But you don't want to be. That's not something to be encouraged.
The motivation for the language extension is to detect bugs, right?
Yeah. Yeah. Oh, yeah, and to also let you do things simpler, like, turn real pointers into self-relative.
All right, well, we did pretty good on the time, so thanks very much.